Kwabena Nketia is originally from Ghana and received his PhD in Germany in digital soil mapping. He has more than 11 years of diversified experience in scientific research, project management, and geospatial data analytics while collaborating among multidisciplinary teams. Presently, he's a research associate in our lab, the Agronomic Crop Imaging Lab. Today's presentation will look at agriculture, big data, artificial intelligence, and the current and future needs of crop phenotyping. Kwabena?
Hi, everyone. So we've heard a lot about big data, and we want to explore ways we could upscale such plot-level research onto a global scale. So I take you through a series of some test case we've run in our lab looking at agriculture in terms of digital agriculture, looking at big data and how explainable artificial intelligence play a key role in meeting some future needs of crop phenology. So the key question is, what has been the occurrence of the terms in using plant phenotypes? And for us in crop imaging lab, we are focusing mainly on the image component, where we look at how images could help us explain research at plot level on a global scale. So now, over the years, research has been driven mostly in precision agriculture. And if you look at the trend, as precision agriculture keeps increasing in terms of publication, we're also seeing a rise in plant phenotype in this direction. And for us, we want to explore possibilities of using these huge data set that has been collected over years and how to translate this into global research purposes. And now, in terms of global perspective of using such data sets, we're also looking at collaborative research across the globe and how such global data sets support sustainable agriculture. So now, what has been the main goal of some of this research? With field imaging, we also have data sets being generated from plant breeding. We have those in economics and insurance. We also have those in-season events to look at drought, flood, and all that first effects on productivity. We also have an understanding of how yield stability and within field spatial variability is also impacting on precision agriculture. The other side is to look at also prediction of crop yield, whether nowcasting or forecasting. So the understanding of collection of all these data sets, huge, requiring high processing power and all that. We want to have a global understanding of using such data set in that also. And similarly, there is also issue with post-harvest losses where such research focus on using plant phenotype. And for us, our goal is to look at how artificial intelligence play a key role in such big data sets. So now the key question for us is that, how do we feel part of the global gap in meeting such demand for current and future plant phenotyping? When answering this question, have in mind an understanding of sustainability and resilience of our agricultural system. So we have a holistic understanding of how we address part of the global questions, and in addition to meeting sustainability and resilience. So now, for the concept of digital agriculture has mainly been about skills and either occurring at plot level, field level, or at regional skills. And for us, we want to look at a global understanding of how these different skills play a key role in sustainability. And in understanding that, we try to also incorporate different heterogeneities occurring across the globe in order to meet the needs of digital agriculture. For plant phenotyping, this has mainly been looking at plot-scale researches. And for us, we are finding ways, innovative ways to try to upscale such plot-level research onto a global scale. And with that, we can extrapolate most of these research, which are quite game changers on a plot level to a global scale in order to meet different agricultural needs. So now what is the, I would say, the linkage between such global approaches and then plot level approaches? if you look at data and protocols, there are common open data protocols and standard in terms of in-situ data collection and how they capture both spatial temporal variabilities and how that is exchanged. If you look at plant traits and skills, there are different multi-sensor synergies and real-time monitoring from different data structures in terms of whether using UAV remote sensing and also plant phenotyping. And most importantly, looking at the modeling component where we use different models to enhance these tools and also integrate data sets, whether from plot level, field scale, or even at regional scale at such high temporal spatial resolution. So for us, it is all about what you see in the image. Whatever you see on the ground and it is recorded in an image, we can work with this. And this is mainly because of different characteristics that you can already find in images. So whether it is water, cloud, plant, whatever you find on the surface that could be captured on an image, we already can interpret such data sets. So now, with this level of approaches and tools available to us, it gives us immense possibilities to measure, to model, and translate such models into managing resources, also mapping different time scale, different spatial resolution of such features. And at the end of the day, we could use such resources to keep monitoring our systems. So now, the key question, which I think is on everybody's mind, is how are we connecting the plot skills to the field skill? And with answering yourself, also have in mind what are the different temporal, spatial, and spectral resolution associated with all the images that we've been talking about the whole day. So now, for us, we are leveraging on the use of artificial intelligence, moving from this plot scale research into global research, whether regional or field scale research. And on plot scale, there are quite a lot of data sets that has been collected by my colleagues, and these are using different UAV images at extremely high resolution data sets, and this already offers limitless possibilities for us to make use of such data at a global scale. So now for artificial intelligence, there are quite a lot of them, which the computer science guys have already elaborated on them. For us, we are using different machine learning approaches, different deep learning approaches, trying to leverage on the inefficiencies and efficiencies of different architecture of looking at data sets and try to create an ensemble stack of such different machine learning approaches. And with this, we enhance the performance of such artificial intelligence algorithms. So now, looking at a case study, here we show you a bit of what we're doing. And here we use such artificial intelligence to try to fill data gaps in terms of spatial and temporal resolution on estimating daily leaf area index for canola. And with this, we're able to address the hurdle of cloud cover in data, whatever shadow pixels and all that within our image using artificial intelligence. And we came up with daily data sets on leaf area index just to help us explain different metrics from crops. So now, what is the concept or what is even behind these images? It is just a bunch of numbers behind the images in RGB bands. And with this, at every pixel location, we can explain what has been the temporal pattern of this pixel location for whatever time we are interested in looking at. And with this understanding, we translate that into remote sensing. So now, for a leaf area index, it already captures the greenness of a crop, the vegetation for over time. And for every pixel location, we are able to model this sequence of how the plant grows or what has been the stages of the plant throughout the growing season. And with this, we can go as far as images are possible. And for such an image at a single location, we can estimate, for instance, what has been the start of the season, peak of the season, length of the season, or even the end of the season. And even understanding on the accumulated biomass over time, just for a pixel location. With that same approach, we can translate that from that single pixel location on the ground into a field level. And already we can tell you across a field, across a region, across every skill, what has been the start of season for this particular crop we are looking at. And this is the results of canola. So we can tell you the start of season for this single location within space. What was the start? What was the peak? What was that the end of that season for that pixel location? And even for that location, what has been the length of season for that area? So we introduced an electrical conductivity map just to give you an idea that with information on start and peak, even length of the season, and even the accumulated biomass over time for a single location, we can relate that to other physical properties like soil properties like electrical conductivity to give you an idea what is happening at this single location within your plot or your original scale. So for us, the opportunity for advanced agriculture starts with a crop which we are excellently doing in terms of the group here. And with this, there are also systems in terms of Internet of Things, data collection, sensors, UAVs, remote sensing images, even data sets from combines already generates huge data sets that are available for us to explain these plot level physical features on a global scale. So now, this forms the big data we already have within plant sciences. And for that, there are quite a lot of already AI technologies that helps us design such decision support systems in order to manage such data sets. And finally, we are automating this process so that this becomes a repeated cycle to generate such huge data set and manage them. Finally, I want to leave you with a thought that we should think global, regional, and not just limit ourselves to the plot level, because there are endless possibilities for us in terms of managing such huge data sets and explaining global context of the data that we find within our context. With this, we can target food security in order to meet site-specific recommendations, crop quality, and also we can forecast now and even forecast for near future what the yields would be based on such level of understanding of data. We also look at specific tailor-made management recommendations which would address issue of mechanization, supply chain, and all that. We can also improve the Internet of Things and data sync collection from different sources of data and still integrate them in most of the things we do. We also look at optimizing input in terms of seed, fertilizer use based on the 4IR, looking at irrigation scheme and even pesticides and herbicides. These are limitless possibilities for us. Finally, we can monitor crop health, whether on chlorophyll, vegetation, whatever it is, as long as we can see them in our images, we have the possibility to go on them. We can look at in-season events, look at pests and diseases, and also crop responses to different inputs based on our treatments. So with this, I thank Steve, who is with our lab, and Tuan, Hansini, Little Steve, myself, the group behind all that we are doing for the group. Thank you.